Okay, so in this class we will learn about that Maxwell-Boltzmann Equipartition Theorem and its proof. So this proof is basically a mixture of classical mechanics, classical statistics, and also up to some extent later on it is carried on by some quantum statistics. So first of all we will see that the classical part of this classical statistics which is used in this part. So first of all we will see this. So here we consider that every gas is contained in a certain chamber, and that chamber has a specific volume, and the particles of the gas can be distinguishable, but they are not same, they are different, but they are having the same property. So these are two main things. Another thing is you cannot change the number of particles, total number of particles, that you cannot change, and the total energy of the system, that is also constant. So you have to categorize those particles, you have to put those particles in some specific energy zone, that is the work, so that you have to do it in such a way such that the overall energy of the system remains in equilibrium. That means, suppose, say, there are n number of boxes, so this is actually n plus 1 number of boxes. So having energy state epsilon naught, epsilon 1, epsilon 2, epsilon 3 and so on, and at the last it is epsilon n. So these are actually fixed energy state. These are fixed energy state. So this energy state within the gas cannot be changed. What you can change is the number of particles. So number of particles within this fixed energy state. Suppose here I have given n0 number of particles, here n1 number of particles, here n2 number of particles, here n3 number of particles, and so on, here nth number of particles. So I have given, so let me do this R, so this will be better. So this will be Rth number of particles. Okay. So you have to put the particles in this way. So that is your work. What you can do, that you can change some particles, you can take from here and give it to here. Some particles you can change from this energy box and give it to this energy box. So you can interchange the number of particles between them, but you cannot change the summation of all these particles. Okay. So okay, let me take it n. I think n will be more convenient. Okay. So because nth energy, so that is more convenient for us. So these are the number of particles that we can give. So here two things are very important. One is that summation of all these n's, that means say r equal to 0 to n. So this is say I equal to 0 to n, ni, that is equal to your total number of particles. So that is the total number of particles that you cannot change, so it will remain constant. Another thing is that, so you can change the number of particles from this box and give it to this box, but the summation of all the particles is always the total number of particles. This cannot be changed. And the other thing is the energy, total energy of the system, that is I equal to 0 to n, and energy is EI Ni. So that is equal to constant, because this is the total energy of the system. So Ni number of, that is the Ni, ith number of house, and the energy of that house is Ei. So the summation of all this energy is equal to the total energy of the system. So that is constant, you cannot change this thing. So these two are preliminary thing, and you can change some of the particles, you can take it from here and you can give it to there. That means change in Ni is not possible. That means you can say delta ni that is equal to 0 or del ni equal to 0. That means there will be change in ni. So say some particles I have taken from here and I have given to this room, but all over number of changes. So you can say the changes all over, the change of ni is not possible. So this is equal to 0. That means say you are taking 5 particles from here, so it will be, so del I will be 5, and you are putting those particles here. So this will be minus 5, this will be plus 5, and so on. So minus 5 plus 5, so 0. So you can take 1 particle from here, 2 particles from here, you can put 3 particles here. So it will be 1, minus 1, minus 2, plus 3. So it will be 0. So del ni equal to 0. So these 3 things are to be remembered while we calculating this thing. Okay. So now how we will put those particles? So how can we determine this number? How much particle is to be kept in a box so that the total energy of the system is maximum? So that is the work. So that is the work done by Boltzmann specially. So this is called Equipartition Theorem. Okay. So we can say that to achieve that, what is required, that say what is the number of way when you are arranging at equilibrium condition, you are arranging a total n number of particles. You are given total n number of particles. You have to make groups. You have to make n number of groups. So one group containing n1, one group containing n0, one group n1, one group n2. So in how many ways this can be done? So from the knowledge of our permutation and grouping, we can say that this can be done in this much way. So this is denoted as ohm. So this can be done in total number of particles, factorial of total number of particles by so n0 factorial, n1 factorial, n2 factorial, and so on, and it will be n factorial. So this is the number of ways in which you can arrange those particles. So this is the number of ways of arranging. Now you have to maximize this thing. Basically you have to maximize this thing, then you can get what is the maximum chance of having the particle in equilibrium. So we can say at equilibrium this will be the condition. So this is the condition at equilibrium. So this calculation, how to maximize this, is not so easy. So let us take some symbolical things. So this will be n factorial, and this can be written as, so this is pi, and here I equal to 0 to n. So pi means this is the product, and this can be written as ni. So once you have to put 1, then 2, and this will be factorial, of course. Yes. So this will be the thing. So in brief we can write it by notation where pi means multiplication. So you have to maximize this. How to maximize this? So take natural logarithm on both sides. So ln is equal to, this will be ln of n factorial and minus ln of pi I equal to 0 to n number of particles ni factorial. So this thing is done. Okay, so we have taken the ln on both sides, natural logarithm. Now when we take log of some product, so it is converted into summation. So this thing converted into this equal to ln of n factorial minus, when we take the ln inside, then it will be in this format. So this will be the summation, and this will be I equal to 0 to n, and this will be ln of ni and the factorial of ni. So this thing, because now this will be summation, because when you take product inside log, then it becomes log abc equal to log a plus log b plus log c, like that. So this is the thing that we are getting from here. Now we require one approximation, that is called Stirling approximation, to solve this. So I am keeping just this bottom line, and from here I am come to the top. So if you see, this is ln of any x factorial. So this can be written as x ln x minus x. So this is an approximation which is called Stirling approximation. So this approximation is valid if x has a large value, especially. So here we are dealing with number of particles. So this approximation can be used in this case. So ln of x factorial is x ln x minus x. So this approximation can be taken into account. So using this, we are getting, so ln of ohm is equal to, so this was our ln of capital N factorial. So this can be written as n ln n minus n. So this is one thing, and that was our minus. So within summation it was I equal to 0 to n, and there were so this will be ni ln ni minus ni. So this is our approximation when we take the Stirling approximation. So this is the condition when we take Stirling approximation. Now we have to maximize this. So we know that for maximum minima we have to differentiate this, and we have to find the when this equal to 0. So that will give the condition when ni is maximum. So for that we are partially differentiating this. So if this is maxima, we know that ln is a function of increasing function if ohm is positive. So this ohm is positive. So if I take ln of ohm, so this, if I maximize ln of ohm as a whole, so this will maximize this condition. So we are taking d of ln ohm. So this will be equal to differentiation of this. Now this is constant, total number of particles and the log of that. So this will be constant minus this. So this will be constant. So differentiation of constant is 0, and minus this is I equal to 0 to n, and differentiation of this thing will be ni into differentiation of this is 1 by ni, and this is plus ln of ni and into 1. So this is the differentiation of this, minus this will be 1 into del ni. So this is equal to 0. So this gives actually, so this is the minus sign. So summation of I equal to 0 to n. So this gives 1 minus 1. So this is cancelled. So this will give this thing into del ni. So this is equal to 0. Or we can say that summation of I equal to 0 to n, and this is ln of ni and del ni. So this equal to 0, because we are multiplying with minus sign, so there will be nothing wrong. So we have to achieve this condition. We have to achieve this condition, but this condition is subject to constraints of two things. That means we cannot overcome those two things. Writing this overhead so that we can understand that what are the constraints. So this thing is our requirement. So summation of I equal to 0 to n, and this is ln of ni, and this is del ni. So we have to make this thing 0. So this is condition number 1, but it has subject to constraints. There are two things we have to maintain while we do this. So one thing is this, that your summation of I equal to 0 to n ni. So this is equal to total number of particles. So this is one thing. So if we differentiate this, then this is a constant. So if we differentiate this, so we will get that summation of I equal to 0 to n, and this is del ni. So this equal to 0. So one is this thing. So this we have to maintain, that this thing is equal to 0. And another constant is this, the total energy is also constant. So I equal to 0 to n. So this is my I. Okay. So epsilon I ni, so this is equal to also constant. That means we have to also maintain this condition that when we take I equal to 0 to n, so epsilon I and del ni, so this should also be 0 because differentiation of constant is 0. That means we have to maximize this thing, keeping in mind that this thing should be 0 and this thing is also 0. That means this is one constant and this is another constant. So we have to maximize this thing. Maximize means we have to find the solution of this thing. Now we have to find the solution of these things. Just we have come to this condition that we have to find the solution of this thing subject to constant, that the total sum of the particle is equal to constant. So del ni equal to 0. And the second thing is this, the total energy is also constant. So that's why, so del ni, ei into del ni equal to 0. So we have to maximize this thing. You have to find the solution of this thing, keeping in mind these two conditions. Now this can be done by using Lorentz. There is a formula for, that is by undetermined constants. We can use Lorentz undetermined constant formula, and that is used generally in this case. So this is called Lorentz undetermined constant. So we use Lorentz undetermined constant here to find this condition to be satisfied. So what we do, suppose this is equation number 1, this is equation number 2, this is equation number 3. So what we do is very simple. We just multiply this, we keep this, and we multiply with some arbitrary constant with this, and we multiply with some arbitrary constant with this, and as a whole we make it 0, and then we try to find out what is the value of those arbitrary constants. So this is the general process of finding. Taking equation number 1. So equation number 1 will be as it is, plus we will multiply with alpha into equation number 2, plus we will multiply another constant beta into equation number 3, and we will make this equal to 0, and then we will try to find out. So these are the multiplication sign basically. So these are undetermined constant, means we do not know the value of these things, but we have to find the value of those things such that this condition holds good. So for that reason, if we take the first equation, so this will be summation I equal to, now you see this is also, all these are containing actually del ni. So these also containing del ni, these also containing del ni. So keeping this del ni outside, we can just multiply I equal to 0 to n. So this equation will be ln of ni plus this will be only alpha, and this will be beta this. So all those things put together into del ni. So this thing equal to 0. So we have to make this condition satisfied. So this is the ultimate condition that we get from here. Now the condition is such that we know that del ni is equal to 0. We already know that del ni is equal to 0. That means if we take del ni equal to 0, then you will not get any solution. So we are taking this, we already know. So we already know del ni is equal to 0. So we cannot use this function because this is already 0. So we have to work with this thing. So if I take this, then ln of ni plus alpha plus beta epsilon I equal to 0. So that means what is the value of ni here? So we are getting ln of ni, that is equal to minus alpha plus beta epsilon I, and the value of ni equal to e to the power minus alpha plus beta epsilon I. So this is the result that is actually obtained by this Boltzmann partition theorem. And after that, we go to some quantum statistics and find the value of alpha and beta. So this is the first part of the equation. But here, when Boltzmann actually approached in classical way, much more in classical way, and he also finds some suggestion of this, some solution of this. So he said that this is some particles having energy, say epsilon. So this can be written as e to the power minus alpha plus beta epsilon. Simply we write it in this way, and this thing will be useful in our next class when we will find the value of alpha and beta. But what Boltzmann actually did is this thing. He said that Ni is equal to, we can write this e to the power minus alpha, and this is also e to the power minus this thing. So we are just breaking this, and we know that summation of this total Ni are equal to 0 to n, and summation of Ni, so this is equal to total number of particles, and that is equal to summation of all these things. That means summation of e to the power minus alpha and e to the power minus beta epsilon I. So summation means here I equal to 0 to n. Now notice that this e to the power minus alpha is a constant. So this is not going to vary with when you are changing from 0 to n. So we can take this out. So he said that we can take this alpha outside, and we can write n is equal to e to the power minus alpha into summation of I equal to 0 to n e to the power beta epsilon I. So the value of e to the power minus alpha becomes this thing. This is n by summation of I equal to 0 to n, and this is e to the power, so this is generally written as ei beta. So he said this quantity, that is summation of e to the power I into beta, this constant over this, so this is generally called partition function. So he wrote it in this format, that is n by p, where p is called the partition function. So p is equal to summation of I equal to 0 to n e to the power ei beta. So this is called the partition function. So that is the thing that he gave. So he wrote that our actual Ni equal to, the formula was Ni equal to e to the power minus alpha and e to the power minus ei into beta. So we have write this e to the power minus alpha as this. So this can be written as n by p and e to the power minus ei beta. So this is the number of particles. This is one of the solutions. And later he classically found that beta is equal to 1 by kVt. So later he found that beta is equal to 1 by kVt, and this value we will find through the quantum statistics, and later he put this over here. So this formula is called equipartition. Equipartition means n divided by p. So just like we are giving partition to energy levels, so total number of particles by this partition. So this ultimately gives a formula which is in this format, that number of particles in any energy box is equal to total number of particles by partition function into e to the power minus ei by kVt. So this was the proof of Boltzmann and later on by Maxwell. So we will see what was the approach of Maxwell. Both approached in the same way, but in later class we will discuss mainly about how to find the value of alpha and beta and what is the quantum statistical approach of this. Okay, thank you.